Yeah, it's pretty. It's raining. Isn't that great? Isn't it just so? Is this just so easy?
Is that rain or is it a train?
It's rain.
It's rain.
Like proper rain now.
Okay.
Yeah, real proper rain.
Yeah. I heard that 2021 was one of the wettest years on record.
I heard that too.
And it rained right up to midnight. In fact, on to the small hours of New Year.
Are you ready to go?
I like the, do you think
Yeah.
so?
Okay.
I think he did. Oh no, there we go. The one in the corner that provides some cash.
Hi, hello. Welcome to a very wet version of Astronomy on Tap Tucson. Woo! Thank you. Yes, very nice of them to support us with this awning and patio. I don't know what you would call this. My name is Logan. I'm one of the organizers here at SpaceDrafts. SpaceDrafts is part of Astronomy on Tap, which is a worldwide network of local shows happening all over the world. So if you're not from Tucson, go back home, check out Astronomy on Tap. There's probably a show somewhere near you. So just to let you know a few things before we get started. So we have a few free giveaways left over from past shows, including James Webb Space Telescope stuff, and there's even a few pictures of a cat dressed up as a princess if you were here last month. There's still a few free giveaways, so please come on up and grab them. And we are also still selling our stickers. They are $2 each. The more you buy, the more cash we'll have on hand to make better merch. So if you want to support us and enable us to buy things like pint glasses and t-shirts for the future, please come up and grab one for $2 each. So we'll have two talks today. The first one is by Sebastiaan Haffert and on the origin of planets and moons. Following his talk, we will have a 20-minute intermission. During that time, please feel free to go grab another beer, tip your bartender, buy a sticker, grab a freebie, or just chat and ask questions. And then we'll start up again with Andy Ryan for our second talk of the night. And we have a tradition here where you may have noticed that sometimes a train will come by and be very loud and interrupt our lovely show. So when that happens, we like to say, choo-choo, and then take a drink. So be prepared, because we will probably be interrupted by a train. Let's see, I think that's all that I had to say. So without further ado, I would like to introduce Dr. Sebastiaan Haffert of Stewart Observatory, one of my research colleagues, a member of my research group, telling us about planets and moons. Take it away.
Thank you, Logan, for the introduction. So as Logan said, my name is Sebastiaan Haffert, and I'm currently in my third year as a NASA Hubble Fellow at the University of Arizona. So I come from the Netherlands, and the Netherlands is quite wet. So I actually moved here to escape the wetness, but it didn't really work out as well as I hoped. So today I will be talking about the origins of planets and moons, and specifically how we can observe them, and how we can observe the process of the formation of planets and moons. However, up to about 30 years ago, we did not really know about anything about planets and moons outside of our own solar system. So 30 years ago, if you would ask an astronomer what planets are there in the universe, they would only give you this picture, our own solar system. Of course, with all the known planets. And since a couple years, it's almost 2 decades now, since Pluto and Ceres have been declassified as dwarf planets. However, in 1992, astronomers were able to find the first exoplanets. So this was a bit of a special system. This is a pulsar, and that's a little bit of a late stage star, so it's very unlike any star like the Sun. And they found 3 small rocky planets around it. And this was in 1992, so that was the year that I was born. So every time I try to remember, when was the first planet found, I just have to remember when I was born. So it's only 30 years old. or at least almost 30 years old. However, since then we have discovered many more planets. Especially one mission that was very successful was the Kepler telescope. So the Kepler telescope was always looking at the same portion of the sky. So you can see here all these squares are the different detectors, are the different cameras that are looking at that specific point of the sky. And they were looking for planets. So this area may seem very large, but it's only 0.25% of the night sky. So if you want to fill the whole sky, we would actually need 400 Kepler telescopes to do a monitor of the whole universe. So what this animation shows you is that at this particular point in time, which planets and where those planets are that can be detected at that point. So you can see at any point in time, you can detect like a couple tens of planets, maybe like on the order of 50. So every time Kepler stares, there's always 50 planets in the field of view. So that's quite a lot. And when you look at the system architectures themselves, so how large are the planets, at what radius do they orbit around their star, you can see that most of the systems that have been detected are quite compact. Because here's the solar system in scale. Oh. So here's the solar system in scale. So you can see that all the other planets are, other planetary systems are quite.
There's no winning.
Okay, let's try it again. So these planetary systems are really quite unlike our own solar system. And that really threw us off as astronomers, because before that all theories about planet formation, about how planets form and how the planetary systems are built up, they were all based on the solar system. And because we detected all these planetary systems that were completely different, that means that also our theories about about planet formation had to change. So this has been a very active research topic in the past 30 years. However, only until a couple years ago having been able to do the actual first observations of formation. So now my first trivia question, because I was asked to add some trivia questions, is how many planets has Kepler discovered to date? So only the Kepler mission.
So I forgot to say this. When the trivia question comes up, please raise your hand. He will call on you, and if you are correct, you will win a free sticker.
So, yes. Yeah?
4,765.
Almost. So, who else want to try? You want to try? A. Okay, so the correct answer was A. So the other numbers. So A is the number of confirmed planets by Kepler. However, there are way more planets that still have to be determined, or at least they are candidates that can be determined whether or not they're planets. So we need follow-up observations with other instruments. So there could be almost 5,000 planets that will be discovered by Kepler, but some of them still need to be confirmed. So this number was just 10,000 times pi. But 941 is the number of Earth-sized planets that Kepler has found in its lifetime. And 417 is the number of planets that are similar to Jupiter that Kepler has found. So actually all numbers are related to the discoveries that Kepler made. So this is quite a lot. However, Kepler cannot help us, or at least it's very difficult to constrain planet formation with Kepler. And the reason for that is, well, first let's go through the stages of planet formation. So planet formation is intrinsically linked to star formation. You cannot make planets without making stars. And that starts all the way in the beginning with a very large, dense cloud of gas and dust. And that large cloud of gas and dust will collapse under its own gravity, and will then collapse. It will contract, and then inside this contracting cloud of gas, you will have dense cores. And from those dense cores, you will get the first stars. Those dense cores, they will collapse further into stars. And then some of the material around the star will not fall on top of the star, but it will fall around the star in a disk. So here you can see a star in the middle with a disk around it. And this roughly happens like, it's quite similar to the process of making a pizza. So you've probably seen movies before.
Oh, choo-choo!
Cheers. So you've probably seen movies before where like pizza makers, they throw up the dough in the air, and then when you rotate it, it flattens down and becomes a thin crust or a thin disk. That's exactly what happens in the universe. Only you need to replace the dough with gas, and the twisting motion is just a rotating star. And then you get this disk. And this disk is where the magic happens. It's a very playful train today. Okay, let's hope it's over. It's fast. No. So we have this disk around the star, and we call that disk the protoplanetary disk. So that's the disk wherein protoplanets form. However, Kepler only searches for this last stage. So in this last stage, this disk has been blown away by processes from the star, and only the star together with the planets that orbit around it are still there. However, to really understand planet formation, we really need to observe this stage. So this stage where we actually see the planets still building up their mass and still building up their size. That's really the stage that we want to see. However, that's quite difficult. Luckily, there are certain systems which we call transition disks. Those are a little bit in between those two stages. And in those two stages, you have giant planets, such as this planet and the planet over there. And they orbit around the star in this disk, and they sweep up the gas and dust, and they create gaps. Because they sort of act like vacuum cleaners. They just go around and vacuum up all the gas and dust. And because they make a gap, we can actually have hope to search for them. And we can actually find them. However, it's quite difficult with ground-based telescopes. So if we use a large telescope from the ground and we want to see these planets, it's very difficult because we look through Earth's atmosphere. And Earth's atmosphere is quite turbulent. So you have temperature changes, you have wind, you have pressure differences, and all these things cause the air to be turbulent. And that's sometimes also something we call what we call the twinkling of the stars. So if you go outside and look at stars, you can see that they twinkle, and that's because of the seeing and the turbulence in the atmosphere. And if you use a large telescope and we look at the star, this is sort of what we see. We see this giant blob, because this is what the atmosphere does. So the atmosphere smooths the image, you lose your spatial resolution, you don't really have that sharpness anymore that you want. And to highlight that, this image is actually an image of two stars, but you cannot really see it because of the turbulence. So what we do in this type of work is we use adaptive optics. So adaptive optics, let's see if it works. Yeah. So we have the atmosphere, it causes a lot of jittering, a lot of smoothing, it is really messing up our images, and we need to use adaptive optics. So in adaptive optics, we measure, so here you see the starlight coming in to our telescope, and we measure the distortions caused by the atmosphere. And then we use a computer to calculate what the best pattern is to counteract the effects of the atmosphere. And we use a miller that can change its shape. and we then apply that shape that we measured, we apply that to the mirror so that when it hits the mirror, it reflects off, we have a nice, flat, corrected image again. And that helps us to get back to recover our spatial resolution and to make sure that our telescope actually can image correctly. So if we go back again, so this is the adaptive optics turned off, so we only see the atmosphere, and we turn it on, we see a much sharper image, and suddenly you can see that there's a second star, which we did not see before if you only look at the atmosphere. So adaptive optics really helps us to peer through the atmosphere and to achieve high resolution. However, the second problem is that we're searching for planets and not stars. And planets are usually quite faint; they're a little bit dim. So in this image, there's a firefly next to the lighthouse that we're trying to find, and that's actually that's quite similar to the challenge that we have for searching for a planet. A planet's very faint, so comparable to a firefly, and stars are super bright, so that's comparable to the lighthouse. So what we need to do, we need to have techniques that we can use to switch off the lighthouse or to switch off the star. So luckily we have these techniques, and they're called coronagraphs. I will not go into detail how they work, but we have techniques that we can use to sort of switch off starlight. And now to leave here question 2. Suppose that you're an alien on one of the other stars and you're looking back to the solar system. If we want to look for Jupiter, we need to know roughly how much fainter Jupiter is or how much brighter the sun is. So if you were looking from another solar system, from another planetary system, and you look towards Earth, how many times brighter is the sun compared to Jupiter? So we have A 1,000 times, B 1,000,000 times, C 1,000,000,000 times, or D 100 billion times.
100 billion.
So we had an answer here, and the answer was 100 billion times, and that's a little bit too faint. Jupiter is a bit brighter. Who had yeah?
I just say 1 billion.
Yeah, that's the correct answer. It's 1 billion. So if we actually compare these numbers, then 1,000 is what you would get if you have a massive star and a dwarf star. That's roughly the contrast. 1,000,000 times, that's roughly the brightness ratio between a planet that's being formed and the young star. So usually planets that are younger are brighter because they're super hot. So you can imagine when planets are being formed, it's quite a cataclysmic event. Yeah, you have all these rocks, all pebbles that smash together. That creates a lot of energy. So the planets in the beginning, they heat up a lot. So the brightness ratio is higher. And when they become older, they cool off and they become fainter. And then this contrast increases. So that's more difficult. So at 1 billion times we have Jupiter, and 100 billion times that's Mercury. While Mercury is closer to the Sun, it's a lot smaller than Jupiter, so it reflects less light, and it's also much darker because Mercury is only stone. It does not have an atmosphere. It does not have clouds. It only has rocks. So it's Mercury is really difficult to see. However, if you look at planetary disks, like if you look at the disk that I told you about where planets form, we can actually see them. So this is the disk, and we applied these two techniques. We applied adaptive optics to peer through the atmosphere, and we applied this technique where the coronagraph, where we turned off the star. And then we can see this disk. However, in this disk, we can also see this blob, and that blob was actually a planet. And this planet is still forming. And to give you a little bit of the scale of how large this thing is, or at least what the distance is, this distance, this bar, represents 113 AU. So AU is an astronomical unit, and that corresponds to the distance between the Sun and Earth. So this is 113 times the distance between the Sun and Earth. So to put that a little bit in perspective, the distance between the Sun and Earth is about 93 million miles, and the distance between the Earth and the Moon is about 250,000 miles. So last month, it was of course big news in astronomy, is that James Webb, our new space telescope, has launched, and James Webb will go to L2, which is 900,000 miles away. However, this is only roughly 1% of the distance between Earth and the Sun. So if you now think back, this is 113 AU. So that's 100 times more than the distance between Earth and the Sun. And if we scale it down a little bit, if you measure the distance, this planet is roughly at 20 times Earth-Sun distance. So that's roughly, we need to, like it's 100 to 2, it's like 2 billion miles. That's the distance, yeah?
How large is the star that it's orbiting?
The star is a late type star. It's a little bit smaller than the Sun. And one thing that I was very interested in is that if this planet is forming, we want to know, or at least this planet is in this disk and we think it's forming, and we want to actually measure the signatures from that. And if planets are forming, that means they're accreting material. So just like how around a star there's a disk, you also have planets with disks around them, and we call them circumplanetary disk. So that's the disk around the planet, but then just in Latin. And this planet has strong magnetic fields, and due to the magnetic fields, it creates this gap. And then these pieces of, or these streams of material, they follow the magnetic fields of the planet, and they fall, and that's what connects the planet with the disk. It's these magnetic fields, and through these funnels is how the material is transported from the disk on top of the planet. And that happens with quite a energetic process. So you have this material that falls with the speed of sound, or sometimes faster, and it creates shocks when the material hits the star. It's similar like how a fighter jet goes through the sound barrier. You get this loud bang, or this shock when it goes through that through the sound barrier. And same thing happens in space. When the material goes through this funnel fast on top of the planet and goes through the sound speed, that's when you create shock waves on top of the planet, and that creates a very specific type of emission. So a very specific type of light. We can actually search for that very specific light. And that's what I did with this instrument. So this instrument is MUSE at the Very Large Telescope in South America, in Chile. So here we have the telescope, which uses 4 lasers, and these lasers are being used to do the adaptive optics. And then here on the side is MUSE. And with that instrument, we were actually able to search for this specific type of emission. And that's where I detect 2 planets in the system. I first thought I was only searching for 1, but apparently there were 2. And I did not notice that the first time, so I reduced the data. I sent this image around to my collaborators. I was like, look, I found a planet. And then they quickly emailed me back, but hey, but there's a second thing. And I did not see that in the first. So, but when I noticed that, I was also quite happy. So this emission, this image that we're showing, you see things light up that are growing. So seeing this emission means that this companion and the other planet that we found are growing. And they are roughly growing, like the amount of material that they grow is about Jupiter. For every like 10 million years, they grow about 1 Jupiter in mass. So it's not a very fast process. On human timescales, on astronomical timescales, it's still relatively fast, 1 million years. But it takes about 1 to 10 million years to gain 1 Jupiter mass. So later, a year later, I went back to the telescope to get more data to hopefully search for more companions. So I got better data. Sadly, we did not detect a third or fourth companion, it's only 2. However, that was still a nice result that we could confirm our earlier observations. And here are the images that we got in thermal infrared. And you can see here's the first companion, and here's the second companion. So the reason why the second companion was not detected there in these first observations is because it's so close to the circumstellar disk. You see the disk edge here, and if you go back, it's so close to the disk edge is that it was believed to be part of the disk instead of a separate companion. And the only reason why we could figure out it was actually a planet is because the disk does not light up in this specific emission. The disk is not growing, it's the planets that are growing. And that was how we were able to disentangle the planet from the disk. However, what we also are interested in is characterize not only knowing how fast is the planet growing, but is there a disk around the planet? So we've detected that it's forming, we are detecting that there's material falling on top of the planet, but where is that material coming from? Is there a disk around that planet? So there were other astronomers that were doing observations with the Atacama Large Millimeter Array, or ALMA. And ALMA can look very good, almost very good in detecting dust. So if there's dust in the system, you just point ALMA at it, and ALMA will find it for you. Or at least, I've been told. It's probably a lot more complicated than just that. And they were quite successful. So this is the image again of the same system. And you can now very clearly see the circumstellar disk. So that's the ring of dust around the star. But then at the place of the second companion, we actually found a lot of excess emission, which is thought to come from this circumplanetary disk. So if you want to know a little bit of how it looks like, so here we have the planet, and then if we zoom out, so this is all artistic impression, this is not observations. You can see the disk around the planet, but here is, for example, a site where moons can form. So just like how planets can form in these disks around stars, that's also the same way of how moons can form in disks around planets. So detecting this circumplanetary disk was actually the first detection ever of a site where we can form moons and where we can find new moons. So that was super exciting. So now I have the third trivia question of my presentation. We're going to do a little bit of an experiment, and we're going to decide whether or not something is a frying pan or a moon. So if everybody wants to join me in the experiment, so if you can stand up, please. If you can stand up, otherwise it's difficult. Okay, so if you think, so we start with the first image. If you think this is a moon, raise your hand. Nobody thinks it's a moon? That's correct, it was a frying pan. So everybody can keep standing. Let's go to the second image. If is B a moon? Please raise your hand. So, okay, everybody that raised their hand is correct. This is Europa. It's one of the moons of Jupiter. If you were wrong, please sit down. I don't know if anybody was wrong, but there were quite a lot of hands that are correct. Okay, third image. C. Is C a frying pan or a moon? Raise your hand if you think it's a moon. Okay, it was a frying pan. Sorry, sit down if you're down. Okay, D. Is D a moon or a frying pan? Again, raise your hand if you think it's a moon. Okay, it's a frying pan. Almost everybody had that correct. And now E. Is E a moon or a frying pan? Raise your hand if you think it's a moon. That's correct. This is Oberon, which is one of the moons of Uranus. And the last one, F. Is this a moon or a frying pan? Raise your hand if it's a moon. Sorry, it's a frying pan again. So I see a lot of people are have it correct. I don't know if we have enough stickers, but at least everybody is very good at this, at distinguishing moons from frying pans.
You were right. You can come grab a simulator.
So, what's now the future of these observations? So the instrument that I actually used to observe protoplanets, so planets that are still forming, was actually not developed to take those pictures. It was actually developed to do galaxy observations. It was not really used for planets. However, this instrument, it's called MAGAO-X, is being built and designed here at Stewart Observatory at the University of Arizona. And this instrument is actually specifically designed to look for the emission of growing planets. So that's also one of the reasons why I moved here and why I started to do research here, is because I wanted to do observations with this instrument. So here you can see MAGAO-X. It's an instrument that ships back and forth, like from the university to the telescopes in Chile, and also comes back so that we can do upgrades. And here you can see it being wrapped up for observations and put in a shipping crate. Here is it, neatly put in the shipping crates. Here's it being installed on the left at the telescope, and on the right it's completely installed and at the telescope. So sadly, this observing run happened in December 2019. And the only tests that were done was to check if the instrument was working or not. So we call that commissioning. So that's just to do tests and say, well, did we meet specification or not? We would have returned to the telescope in April in 2020. That did not happen due to COVID. So, like fall 2020 also did not happen. Sadly, spring and fall 2021 also did not happen due to COVID. So our next chance is April, so 2 months or 3 months from now. So let's hope and pray that this time we will be able to go to the telescope again and to do actual observations of these growing planets.
It'll happen.
It will happen, hopefully. So the takeaway message from my presentation is that nowadays we can directly image young planets that are still building up their mass. These planets have their own disks, and in these disks moons can form, and hopefully future instruments and telescopes will be able to do better characterization of these systems, and hopefully we will find more of them. Thank you.
Questions?
Or comments, or if you have a joke, that's also good. Yes.
What wavelength do you see the planets using material?
Yes, good question. The question was, at what wavelengths or what type of light do you actually see the planets growing? The light that we're specifically looking at is called hydrogen alpha radiation. So that is radiation that's created by hydrogen. And it's a specific energy transition of hydrogen. And that happens at a wavelength of 656.28 nanometers, which is a little bit of a dark red color.
Why does looking at H alpha light show you that it's an accreting protoplanet that's growing? Like, why do we look at H alpha to look for growing planets?
That's also a very good question. So the reason, so Logan was asking, why are we looking at H alpha and not at anything else? So the reason why we're looking at that is because H alpha, it's due to this shock. When the material falls into the planet, the shock becomes very hot. It can become like hundreds of thousands of Kelvin, so 100,000 of even Fahrenheit. It doesn't really matter anymore at that point. And due to that heat, you have all the atoms inside these shocks. They completely break apart, so they all become ionized. So that means that they lose their electrons. And when the gas cools down, when it reaches about the temperature of about 10,000 Kelvin, or now I have to think a little bit, I guess it's about 20,000 Fahrenheit, right? I don't know. That's the moment when hydrogen starts to form again. And that's the main reason actually why we see hydrogen first, is because it's the first atom that really starts to recombine again and starts to emit light.
Other questions?
What could this tell us about our own solar system?
Sorry?
What could these results tell us about our own solar system?
Yeah, so what can these results tell us about our own solar system? So one of the things, this will take a while. Yeah, so what we actually found is that these planets are not simply orbiting their host star. They're orbiting actually in a very specific ratio. We call that orbital resonance. And what that means is that this inner planet makes 2 orbits for every time the outer planet goes around once. So it's the outer planet goes around once and the inner planet goes around twice. So we think that's also something that happened in the early stages of the solar system, where Jupiter and, now I need to remember, Saturn were orbiting. So they moved in to our own solar system, and we think that during the early stages, Jupiter and Saturn also moved together like these companions. So they also had this orbital resonance. And due to that orbital resonance, they moved in a very specific way through the solar system, which disturbed all the other planets into their current orbits. However, there was never really any confirmation that that specific type of configuration, like this orbital resonance, could happen. So this is also the first detection. So these two are actually the first planets we ever detected in a disk, and also the first planets we ever detected that were still growing. So they're also the first planets that we found in this orbital configuration. So it's all quite new. And actually every new direction helps us constrain all the theories. No?
Why is millimeter wave useful for detecting gas?
So millimeter waves are useful for detecting dust. So generally, if you want to look at something of a particular size, you need to use a wavelength. So the wavelength of light needs to match that size. That's like a rough like guideline that you can use. So if you want to look at dust is like they're like piece of a couple millimeters. So you use millimeter waves to look at it. And so this is thermo-infrared light, and this disc here, this part of the disc, that's scattering from micron-sized grains. So those are really fine grains, and that's also exactly roughly the wavelength that we're using here. So this was taken with a wavelength of about 2 microns.
Any last minute questions? All right. Give Sebastiaan. Oh wait, there's one more question.
I have a really silly question.
Sure.
How did you get such good pictures of frying pans?
How did I get such good pictures of frying pans? So, well, actually, I didn't, but it's this photographer, Christopher Jonansen, from Norway, who took these pictures and figured out they look quite a lot, or at least he took these pictures, and then NASA figured out that they look quite a lot like moons. So NASA was actually, so I can say, I cannot claim to came up with this idea. It was NASA that came up with the frying pan or moon idea.
Love it.
Yeah.
So if we can't use the instrument anymore, can we observe frying pans instead?
Sure.
Your PhD in frying pans.
Yes.
Okay, thank you all.
All right, so now we'll have a 20-minute intermission. It is currently about 7:40, so we'll come back at 8 o'clock. Please feel free to grab some stickers and some free things, and et cetera, et cetera. Grab some more beer, tip your bartender. See you in 20.
So, my friend the kid has a planet talk with science and technology. The first question he got at the end of it was, what is an exoplanet? Because he had failed to define it, and he had used it for, I don't know, a good 30 minutes.
I have it up so I can just...
It
There it
was
is.
so crestfallen at the end of it. It was like... will be pulled again in a minute, so preemptive They're related. So hopefully
It's just really great. Bye.
Good time.
Oh, nice.
I never ask that question because I know that I keep these
All right, if everyone wants to find your seat, find your beer. We are ready for talk number 2 of the evening, which is given to, which will be given by Andy Ryan from Stewart Observatory's Lunar Planetary Laboratory.
University of Arizona's
Excuse me, what did I say?
Stewart Observatory.
Oops. University.
The subsidiary of Stewart Observatory.
Oops. Let me try that again. Today, the second talk will be given by Dr. Andy Ryan of University of Arizona's Lunar Planetary Laboratory. Please give him a round of applause.
Thank you. Get myself situated here. All right, so tonight I'm going to be giving a little bit more of a planetary science talk, and I know that these are more astronomy-themed lectures, so I promise I will include some telescopes and astronomy-related objects within the talk. So I titled my presentation Glowing Planets because if you think about it, really all objects are glowing in the thermal infrared. Anything with a non-zero Kelvin temperature, which is just about everything, should be emitting infrared energy. And so in a sense, all of the planets in our solar system and elsewhere, and our moons, which is shown here, so this is an infrared image by FLIR of our moon, showing the different areas, the different hot spots that are lighting up, and some areas are cooler. And so we're going to talk a little bit in this presentation about why we see these differences in temperature across the moon. What's causing all those little variations there? And I was told not to include any plots in this presentation. I put a couple in there. I'm sorry. All right, now that I've spent 5 minutes on the cover, the title slide here, let's jump into it. So, actually, no, let's wait here. I wanted to say something else. I'm going to be telling a little bit of a history story embedded in this, but I realized initially I wanted to start at the beginning and then work our way forward, but I realized I kind of have to tell the end first, and then I'll go back to the beginning. So I'm going to tell the ending, and I'm going to try to end with a little mysterious, sort of intriguing point, and then we'll go to the beginning, and I'll save the solution for the ending. So hopefully you'll all be waiting with bated breath for that. So first, the ending. How do we use temperature measurements of planets?
Great timing.
Choo-choo.
Great timing. Thanks, Jenny.
The train's like, get on with it. All right. Can you all hear me? Good to continue? All right, so how do we use temperature measurements in planetary science today? So I have to explain something called thermal inertia. And so I'm gonna throw the technical stuff right up front in this talk and just get it out of the way, so hopefully we're all on the same page and I can use this word thermal inertia and you all know what I'm talking about. So thermal inertia, it's all in the name right there. Thermal meaning temperature, and inertia is a resistance to change. So a thermal inertia of a planetary surface is just describing how resistant is it to a change in temperature as you have the rising and the setting of the sun, which causes the surface to be periodically heated. So the analogy that I always like to talk about is a hot beach under the sun. And I think, unless you've never been to a beach, in which case I'm sorry, we've all probably burned our toes on the hot sand once, and you're just sprinting to your towel or away from your towel or get into the water as fast as you can. And that's because of the properties of the sand and the way that it is absorbing heat from the sun. And so if we look at this beach sand scenario, we have our sun here, and it is emitting light, which is hitting the surface of our sand. Some of that's getting reflected, but quite a bit of it will be absorbed and converted into heat, into thermal energy. Now, the sand is not very good at dissipating that heat quickly. It doesn't absorb into the surface very fast. And because of that, you'll end up concentrating a lot of that heat very close to the surface. It gets stuck there, and it isn't able to conduct down into the depth of the sand. And so as a result, the surface will become very hot. And so if you were to look at that with an infrared camera, it would look very hot. But if you stick your toes just down a few inches, you'll discover that the sand is quite cool, just maybe 3 or 4 inches below the surface. Now let's consider a surface that's solid bedrock. Now the rock is much more efficient at conducting heat more rapidly as you have the sun heating it from above. So that heat is going to be distributed more evenly through the rock, and the net effect is that it won't get as hot as quickly compared to the sand. And so if you were to walk on a solid rock surface under the sun, it won't be quite as hot. And kind of the reverse situation is true at night. During the day, the sand-like materials will be hot, rock will be cool, and then at night it's reversed. The rock will retain some of its heat, and the sand will get cold very quickly. Maybe you've experienced standing next to a brick building at night after a really hot Tucson summer day. You can sometimes feel the heat radiating off of the brick still. That's this principle in motion. So here's my first plot. So this is showing different materials with different thermal inertias. What we're looking at here is time on the x-axis. This is actually for Mars. It could be equally well applied to another planetary body. So we have the hour on the x-axis and the surface temperature on the y-axis here. And what I'm showing is different temperature curves for different types of materials that have different thermal inertias. And so a lower thermal inertia material, something like dust or sand or pebbles, will get quite cold at night and then rapidly heat up during the day and become quite hot. Whereas rock has a higher thermal inertia. Remember, inertia, resistance to change. So that change in temperature is going to be more muted, more subtle, where it doesn't get as cold at night and it doesn't get as hot during the day. So we'll be coming back to this throughout the talk. So how do we use thermal inertia? There are a lot of different ways that we use it, but in principle, you can use it to infer things about the surface material properties that maybe you couldn't see with an optical camera, unless you've got a really excellent camera that's able to give you really high resolutions. So this is an example. This is the landing area for the Curiosity rover that's currently roving around on Mars. This is a mountain down here. These are some sand dunes. This is the floor of a crater. This is all within a very large crater. This is a visible image. So this is with the wavelengths of light that we see with our eyes. Now if we convert that to infrared, different things pop out that you didn't see before. So I'll go back and forth a few times. Particularly in this area up here, just north of those dark sand dunes, we see that there are some differences in the surface materials that you wouldn't see in the visible. I'm guessing what we're seeing here, so this is a nighttime image, warm at night, low thermal or high thermal inertia, so that may mean that the soil there is maybe cemented together, so it's kind of like a solid rock. Here's another nice example, and this is pretty relevant to University of Arizona. So the Phoenix Mars lander was going to the polar regions of Mars. Now this is a U of A-led mission that went in around 2007. This is a high-rise image, a very high-resolution image. Here's a scale bar, I think it says about 4 kilometers there, of one of the candidate landing areas. All those dark things you see in there are actually boulders. So there's a tiny little box there, it may be hard to see. That's this image here. All of those little round things, those are truck-sized boulders. You wouldn't want to send your lander there. And then for comparison, this box B over here, which is in one of the lighter toned areas, it doesn't have any of those boulders. It just has this textured pattern on the ground, which is perfectly safe to land on. It's just due to freeze-thaw processes, creates that elephant skin pattern. That's a whole PhD dissertation talking about that. So a very intrepid team of, I think, undergraduate students went and counted every single rock in this image. I think it was tens of thousands of boulders. And they made this map here where the colors represent the abundance of boulders. So red means there's lots of boulders, green, not as many. You can do the same thing with a single infrared image and calculate the abundance of boulders just based on the thermal properties. Remember, boulders should have a very high thermal inertia, and the sand in between them should have a low thermal inertia, and there you go. You have basically the same map. So infrared images of the surface of Mars have been used for basically every single Mars lander past Viking, and they help us to infer the presence of hazards and also help us to predict what the properties of the surface are going to be like. All right, so it's quiz time. If you have a low thermal inertia surface and you're looking at it in midday, so around noon, will it be colder, warmer, about the same as compared to a high thermal inertia surface? So low thermal inertia, dust, sand, and pebbles. Is it hotter during the day compared to high thermal inertia, or is it the other way around, or are they about the same? Does anyone remember? Yeah?
How long is the day?
We'll say, well, it shouldn't matter. It depends on how far down the stuff goes. Let's say that these materials, it's to infinite depth. So at that point, it doesn't matter how long the day is. Do we have an answer?
Anyone have a guess?
Yeah?
Don't be scared.
You're right. It's going to be warmer. Up front. Nice job. All right, so he's right. It's going to be warmer, and here's that plot again. So low thermal inertia, remember low thermal inertia. Inertia is resistance to change. So it has a low resistance to change, so that temperature is going to swing more rapidly. So I want you guys to remember, dust and sand, we think normally it should look hot during the day. Remember that. We're going to be looking for that pretty soon here. Actually, we're going to be looking for it right now. So I'm going to introduce the OSIRIS-REx space mission. Most of you have probably heard this. This is another one near and dear to the hearts of University of Arizonans. So in a nutshell, the OSIRIS-REx mission is an asteroid sample return mission. Its main objective was basically to go to the asteroid, orbit it, understand it, and then locate and retrieve samples. Those samples need to be granular. It was designed to accept particles smaller than about 2 centimeters in size and bring those back to Earth. So we needed to go there and find dust and sand and pebbles. Thermal inertia is going to come back to that. So what did Bennu look like, the asteroid? Well, before we got there, we knew a few things about it, but not a whole lot. We had a rough idea of its shape, although I used to like to joke that maybe we didn't know as much as we thought we knew about the shape. But we thought, it probably looks like this, and we had measured its temperature with infrared telescopes, including Spitzer and others, and estimated its thermal inertia. This is kind of where it falls in the spectrum here of different thermal inertia values, with Bennu sort of in the middle here. These are in thermal inertia units. They're very cumbersome, so we usually don't write them. This is the only situation where I think it's acceptable not to give your units. So, for reference, 1,000 to 2,000, those are our boulders and bedrocks. Coarse pebbles, sand, and dust. So we think, Bennu, it's probably going to have quite a few areas with some low thermal inertia materials just based on that value. So we were feeling good about that. We said, all right, I think we've designed our sample grabber the right way. We're going to find a lot of areas with 2 centimeter and smaller sized particles. And so we got there and we looked at it and we said, well, there's a lot of big rocks. Well, that's to be expected. We had a feeling it's a rubble pile asteroid, so it's just a bunch of rubble loosely held together. We expected rocks, but it looks like there may be some regions that look smoother. They may have fine-grained material that we could sample, so that's great. Let's collect some infrared data and see if we can find the low thermal inertia areas. So the first data set we collected was 12:30 p.m., midday. We're looking for low thermal inertia fine particles, so we're looking for the areas that are warmer at that time of day. This was a plot that I pulled directly from one of the first daily downlink meetings. I kind of went back in the archive and found, where did we first see this presented to the team? So this was presented by the thermal emission spectrometer PI, Phil Christensen, and he said, here's a plot that we just got 12:30 p.m. temperatures as a function of latitude, and hey, look at that, there's this warm area popping out here. We're all like, yeah, that's going to be the regolith area that we're going to sample. That's good. Where does that correspond to on the surface? Turns out that was corresponding exactly on top of the largest boulder on the surface of Bennu. So we were confused, to say the least. We said that is literally the opposite of what we expected. Boulders should have high thermal inertia. This is telling us that the lowest thermal inertia area on the whole asteroid is this boulder. We ran our thermal model, we calculated thermal inertia, we did our due diligence. This was the map we got. There's that boulder. And all those smooth areas have high thermal inertias. The map was the opposite of what we expected. And we kind of had a mystery to solve there. First of all, we realized, like, all right, this is not going to help us find the fine particle regolith that we want to sample. Sorry, Dante, you're going to have to find it somehow else. We're just going to try to figure out what this means. So what happened here? Well, let's go back in time. So I want to talk about the origins of infrared planetary science. Infrared planetary science as it's used to interpret the properties of surface materials, specifically. I'm not going to talk about spectroscopy today. That's a whole other interesting topic that deserves its own lecture. So the temperature of the moon during an eclipse was measured in the 1920s. Let's think about what was known about the moon at that time. So this was, of course, long before Apollo had gone there. We knew that the moon had craters, of course, but at the time, the prevailing thought was that the craters were mostly volcanic rather than impacts. So we didn't really know much about that. And I don't think that we really had a good idea of what the regolith on the moon was like. We've all seen those photos of the astronauts' footprints and the fine powder. That was not really known at this time. So the moon had a lot of mysteries. So these two gentlemen, Edison Pettit and Nicholson, developed a very sensitive thermocouple for measuring the temperatures of stars and planets within our solar system. A thermocouple is basically it's a type of thermometer, and they embedded it in this vacuum chamber, or this vacuum glass vessel here. They had it at Mount Wilson Observatory, and they used the 100-inch telescope there to collect temperatures of stars and planets. I don't think they were the first people to do this, but they were the first to develop a consistent program of infrared astronomy. So one could maybe say that this program really was sort of the dawn of infrared astronomy as we know it today. They measured a lot of interesting things. One of their early measurements was the temperature of Venus. They were able to measure the day side and the night side, and they found that they were both about the same temperature and that it was quite warm. That led to some interesting and sensational articles. Said, well, definitely better than Mars. They measured Mars. They said, well, it's quite cold. I thought this was interesting at the bottom. You know, they said this device can measure a candle from 100 miles away. I don't know if that was an exaggeration or not. Probably not. Their thermocouples, they were building them by hand and they were extremely sensitive. But it's crazy to think of how they were collecting their data. This is a plot of the raw data from the galvanometer that they were collecting. And so these deviations are basically related to the temperature. So in the middle, that's kind of your baseline value. And then the further you are away, the stronger the temperature signal is. They would first take a measurement of total radiation, and then they would put a water cell in between the incoming energy and the thermocouple. The reason they did that was because the thermocouple was being heated by a combination of infrared and visible. And water is opaque in the infrared, so basically this is total energy, this is just visible. So really they're measuring the difference between those two sets of curves there. So these are data for a few different stars with known outputs, and they were able to use those to calibrate their thermocouples. So it's pretty interesting stuff that they were doing there. So they measured the temperature of the moon during the lunar eclipse in 1927. This solid black line is the one to really focus on here. So those are their temperature measurements, the little points on there. And as you can see, the eclipse starts, you reach totality, and you kind of reach this sort of steady decrease in temperature, and then the eclipse finishes there. And this is where it gets really neat. it was actually in a conference proceedings. This is the first instance I could find in the published literature of anyone using temperature measurements to infer the properties of a planetary surface. From 1928, this was a paper read at a conference, which we don't really even use that terminology anymore. No one's saying, I'm going to go read a paper at a conference. It's just simply called, What is the Moon Made Of? I love it. He does some simple calculations. He says Pettit and Nicholson took these lovely measurements during an eclipse. Here's an equation that should describe how the temperature would change. Here are the values I got, and it follows that the surface of the moon could not be made of any solid rock known on Earth, but must consist of some highly porous material, comparable in thermal qualities to a volcanic ash. It's pretty close. A couple of years later, Pettit and Nicholson published their own more detailed analysis of their data. They referenced that abstract, and they said it could be a pumice or a volcanic ash. The second one is pretty close. So they figured out that the moon was covered in powder in 1927 from a temperature measurement, and I think that's just really cool. But I think it's also worth reiterating, they didn't just say, this is the only possible answer, it's only an ash. They also said, well, it could be a very porous rock like pumice. And that brings us back to OSIRIS-REx. Through this whole talk, I've been saying low thermal inertia means fine grains like ash or powders or sand or pebbles. Well, what if it also could be just weird rocks? Like pumice, very porous, very unusual thermal properties. So, is this what's on Bennu? And we were certainly aware of, the existence of these types of rocks. We just never considered, okay, could the asteroid really have pumice or scoria? These are volcanic rocks. They form under a very particular set of conditions where you have a pressurized magma, it erupts, it had a lot of dissolved gases in it, and when you relieve the pressure, just like when you open a can of soda, the bubbles grow and then the glass quenches and you solidify it and you preserve all those little pores. This is not a process that really makes any sense when we consider the formation of an asteroid like Bennu, so we just never thought, okay, but you're not going to find pumice or volcanic rocks on there. We were thinking we would see something a little bit more like this. This is a carbonaceous chondrite meteorite named Murchison. And just as we were getting close to arriving at Bennu, new studies were coming out showing that these rocks actually do have somewhat lower thermal inertias than we thought compared to other rocks, but not as low as what we see at Bennu. They do have lots of small pores in it, like these pores here. These are so large you can see them with your eyes. These rocks also have pores, but they're much, much smaller. They're on the nanoscale, so you can't really see them, but they're there and they do affect the thermal properties. So this is now kind of what we expect. We think, well, this may still be close in terms of the mineralogy, but the porosity must be really, really high to explain what we're seeing on the surface of Bennu. So let's come back, kind of explain our mystery. Why does this map seem like it's inverted from our expectations? Why is the biggest boulder on Bennu a low thermal inertia, and the other areas that appear smooth, they have high thermal inertias? Well, it's actually rocks all the way down. Like, there are really no areas, except for the one area where we collected our sample. There are very, very small areas that have fine regolith particles. Pretty much everywhere else, it's just meter scale and larger boulders everywhere. And so most of this map here, it has nothing to do with boulders versus pebbles and dust. What it actually is telling us is that it's boulders versus boulders. There's just different types on the surface, and they're all weird. They're all really low thermal inertia, lower than we expected any rock could be. And so we identified there are generally two different rock types on the surface. There are these lighter toned ones with the smoother surface, more rounded. And then there are these darker toned, hummocky, we call them cauliflower texture rocks. They have different thermal inertias. This one is slightly higher, this one is slightly lower. And so that map, it's really just showing us the distribution of the different rock types. And the reason that the areas that look like they have lots of rocks have low thermal inertia, it's because these two rocks also come in different sizes. These ones tend to be bigger, these ones tend to be smaller. So wherever we see really rocky areas, it's these ones. And that's why it looks like it has a low thermal inertia. And the areas that originally appeared smooth, although I told you that they're still covered in rocks, just smaller rocks, it's more of these types of rocks which have higher thermal inertia. So that really explains the map. It also tells us that we're going to get back something that we don't think we have in our meteorite collections. These materials are probably very porous, which means they may be very weak. A material like this may not survive atmospheric entry. And so we may be actually bringing something back that could never naturally deliver itself to Earth because it would burn up during atmospheric entry. So sample analysis will tell what is up with these rocks, why are they so porous, what does that tell us about the origin? We've got about 613 days to go. I'll let you know, and I'll come back. All right, thank you. Happy to take questions. Yeah?
So you said you took the first photo at 12:30 p.m. Is that venue time or Earth time? Or
So-
how does it work?
So the question was the first temperature map was 12:30 p.m. Is that Bennu time, Earth time? So that's Earth time. We usually, when we show these temperature maps, we convert it to a 24-hour Bennu clock. Really, Bennu's day is only about 4.5 hours long, but we humans are so used to thinking about, you know, our 24-hour cycle, we usually just convert it to that. Yeah.
How did you ultimately find a place to take the sample?
So, so how did we ultimately find our sample site location? So it was really difficult. We, as a team, were just poring over all the highest resolution images that we had, picking out any area that looked like it had a concentration of visibly, like just to the eye, small particles. And then it was just a process of kind of narrowing it down. They had like the Sweet 16, they had the Final Four, and we ended up with the Final Four sample sites based on not just the appearance, but also the spacecraft navigators were able to do a lot of calculations of likelihood of success in terms of navigating to that particular spot. Some areas looked great, but they had massive hazards, like a giant boulder right next to it that we could accidentally crash into. So we said, well, we can't go there even if it looks sampleable. And so once we got to the Final Four, we did a series of lower altitude reconnaissance passes where we collected even higher resolution data. And it was those data that enabled us to determine if the areas were sampleable and relatively free of hazards. Yeah?
How long is the reconnaissance arm on the actual probe?
So how long is the tag arm? So this is, I should have said this is the end of the tag device and the arm is kind of going off there. I don't know the exact number, but I want to say it's on the order of, it's probably 1.5 to 2 meters, something like that. Like it sticks out a little bit. It's at least 1 meter long. Yeah?
How long was it in contact with it?
It only contacted so how long was the tag head in contact with the surface of Bennu? It was only a matter of, I think, about 10 seconds. It was pretty quick. It came down, touched the surface, it ejected pure nitrogen gas to basically kick up the regolith and stir it up so that it could sort of fly into those gaps in the head there. And yeah, it was only touching for a few seconds. You can find a lot of good videos of that moment. It looks like a bomb goes off because the surface is very weakly held together. The gravity environment, it's micro Gs, and we also found that the cohesion is very low, so there's not much holding this stuff to the surface. We ended up going down, like literally burrowing down into the surface, I think about 1 meter. We went pretty far down before we backed away. How much sample did we get? So our baseline requirement was 60 grams. We think we got about 250 grams. So we're pretty happy with that. And this image here with little bits of sample kind of leaking out is a testament that, we went away with a pretty good haul and they stowed it away pretty quickly after these images were taken here.
I have a question. Can you tell us a bit more about that first map of the moon that you showed on the cover page? Like, what are we seeing in the different regions?
Yeah.
Because there was one really bright spot in the bottom.
So the question is, can we talk a little bit more about the map of the moon? We'll see if I can get there.
You can go all the way back to the beginning.
On the first slide.
Yeah, sorry. It just is a really cool map.
So I think this map.
Like this.
Yeah. So I'm pretty sure that this map must have been taken when the moon was in the new moon phase. So none of it was illuminated by the sun. So what we're looking at here, there's no, this is nighttime. This is all nighttime. So the hotter areas at night are going to be higher thermal inertia areas. I think the reason that we see a lot of craters pop up is because when you have an impact, you raise a crater rim and you excavate a lot of boulders. And so we're seeing high thermal inertia areas because those are boulder-rich areas with fresh exposed rock.
Last minute questions.
Yeah.
Was infrared analysis part of the determination for landing sites on the moon?
Was infrared analysis part of the determination of landing sites on the moon? For Apollo, I don't think so. I don't think we had maps at that fidelity yet. That's a good question. It's not something I've read about, and I've not heard about it, so I think the answer is no. Mm-hmm.
Is the logo on your shirt a real Osiris-Rex logo? Or?
So is the logo on my shirt a real Osiris-Rex logo? This is an older one. I don't think it's official anymore, but we still occasionally make shirts and stuff with it because we all like it.
All right. Thank you. Oh, wait, what? Sorry again. Last question.
Okay.
Sorry, I cut to you
In
twice.
1990, they collected samples of solar dust, and its recovery was not, let's say, well executed. How are you recovering your dust once you get back to the Earth?
So how are we recovering the samples when they come back? So the spacecraft is going to fly past the Earth and basically deploy a drop capsule. So it's a similar method. The capsule does have a heat shield and a parachute, and it's going to come down in the Utah desert. So it is a similar return method, but we just have to trust our engineers that they did their jobs and that it's going to work all right.
Put the parachute in the right way?
I think so, yeah.
All right.
Thank you.
Wow, that was great. I definitely learned a lot from that talk. That was awesome. Thank you. All right, that's our show for January. Please come check us out next month. I forget the actual date, but it's the third Tuesday of February. We'll be right back here with 2 more talks for you. I have yet to finalize exactly what those subjects will be. Once again, please pick up some stickers. There's still some free stuff left over. Tip your bartender, and have a wonderful evening. I'm so sorry about that. I couldn't reach you during the time, so I will give you it to you. Square or circle?